Hi, everybody. Let's talk about DEMs of difference. But first, a quick review, a pop quiz, if you will. All right, here's a ridge line with the hill slope going down to lower elevations, right? If we lay a raster grid over this and zoom in on it, I want you to estimate what the cell value would be in this cell for both a flow accumulation raster and a flow direction raster. So to prompt you with flow direction, I'm giving you a couple different options over here, and I'm just wondering if you guys can remember the difference between flow direction and aspect, and if you can tell the difference between the legends for those. Flow accumulation, if you can just go back and remember, what does flow accumulation mean? Like, how do we define what that is? And what would you guess the flow accumulation value would be for this cell? And I'm going to pause for a second, think about it. Is that an awkward enough gap of time for you? The flow accumulation value here would be 0 because it's sitting at a ridge line and there wouldn't be any cells flowing into it. It's possible that, maybe some trace amount would be, but generally speaking, flow accumulation value here would be 0. There are 0 cells flowing into this cell. For flow direction, this is the flow direction legend. This is aspect. Aspect is the circular set of compass degrees, angles, compass angles measured in degrees, where north is both 0 or 1 and 359. But flow direction is it's kind of a categorical almost direction that water, quote unquote, water would flow out of the cell. And so for this one, it would be predominantly 64, maybe 128. And the point isn't to know which one it is, but to be able to identify that this is flow direction and that because the quote unquote water would be flowing down this direction, it would be going one of these ways. All right, let's get into DEMs of difference. Don't get freaked out that I put this in graph form. I'm just trying to show you that we're looking at it in plan form. No, profile, sorry. We're looking at it in profile. So here's elevation differences and lateral space. And so our LiDAR surface, which is what we're calling, the closest thing to truth that we have, is in green. And in this example, I'm showing the autocorrelated surface. So it's fairly similar in resolution, but I want to make sure that we're clear on the difference between resolution or cell size and accuracy. Resolution is related to precision, how precise, and of course a bigger cell is less precise, a smaller cell is more precise, but that's completely distinct from the accuracy. The accuracy is how true the number is that it's storing. So precision is how many decimal places are we going to include? But what if the cell value isn't even the right value at all? And so what I was hoping that you would see when you differenced these two surfaces is a distribution of differences between the two surfaces, where sometimes the autocorrelated is going to be above our LiDAR surface, and so that would have a certain color or range of positive values maybe, and then a set of negative values where the autocorrelated surface dips below our quote-unquote true surface. When we compare it to the USGS data, so the USGS data is lower resolution, it's less precise, but it's more accurate. That was the take-home message of differencing all these DEMs. The 10-meter data and 30-meter is technically more accurate. So it does a better job of aligning with the actual LiDAR surface, even though the resolution, the precision, is much lower. And I want to draw your attention to peaks and valleys. Peaks are places where the 10-meter data tends to fall short, and in valleys, it tends to be a little bit higher than the LiDAR surface. And this is why. Some of you did a really great job of articulating this. With the LiDAR, let's just say it's 1 meter just to make it easier. 1 meter is going to give us a much smaller area, and it's going to give us a more precise measurement of a peak because we're averaging over a smaller area. If we spread a 10-meter cell over that same peak area, we're taking a 100 square meter area, which is going to have more lower elevations, drawing that average elevation down. So our peaks, when we're looking at a larger cell size, our peaks are going to draw lower because the average is going to be brought down. But then the exact same thing is true for our valleys, where if we have a bigger cell size, we're going to have more higher elevation values, bringing the average for this wider cell, we're going to be bringing that up. So we would expect to see our biggest differences in elevation between the 10-meter USGS and the LiDAR happening at peaks and valleys and places where there's the most extreme change in elevation over space. Just bringing that out one more step to a 30-meter, we would expect it to be smoothed out even more. So if this is a 10-meter cell, we're bringing that peak down because we're averaging over a broader area where we've got a lot more lower elevations that are going to bring that down, and same goes for the valley bottoms. Oops. So this is just kind of showing how on a 30-meter that landscape or that detail is going to be kind of smoothed out because we're averaging over a bigger cell. Okay, so this is an example from Christopher Duff, who I think did a really glorious job of consuming this information and presenting it in a way that really captures the differences between these DEMs. So in this first set of this first set of maps, same scale and extent, really important when we're doing side-by-side comparisons. We're showing here the LiDAR hillshade, and here the 5-meter hillshade. And I know that because I recognize this kind of mercurial interpolated smoothing where we've got all the detail here. We're not just looking at a lower resolution, but actually a whole different surface where it's pooled and smooth. This is interpolated because with the aerial image, the ground can't be detected. So we've lost all of this great detail in here. So we can see places where the LiDAR is both higher and lower. And this is another thing that Christopher did really well. He was very explicit about what do these values mean? What does a positive value mean versus negative? Negative, the blue areas are where the LiDAR was lower than the autocorrelated surface. And we would definitely expect that in the valley bottoms where vegetation is going to obscure. But it looks like when they interpolated this, they really just kind of lost all the detail and smoothed this whole thing over. This whole ridge line got lost. Anyway, the other example that he pulled together shows what I was trying to demonstrate before, where ridge lines or ridge areas tend to be smoothed over between the 10-meter and the LiDAR. And valley bottoms tend to be brought up. But the place that he's drawing our attention to here is this little ridge where we've got extreme change in elevation. The bottom of it, where it would be concave, it's showing that the LiDAR is lower than the 10-meter, which would make sense. That's that valley bottom idea. And then as we climb up and hit the ridge, the more convex surfaces are being smoothed over, and the LiDAR is actually showing as higher than the 10-meter data. So this is a really great example of the results that I would hope that you would get from this. Now, having said that, there were a lot of ways that this could go wrong. I read a lot of different errors people ran into. Everything from my computer blew up when I tried to resample the 10-meter down to the half-meter fair. With one tile, I would hope that wouldn't happen, but it's definitely something to be aware of. This is a lot of processing oomph. Another thing that I saw a lot of that we also ran into in class is this kind of systematic offset. I'm going to pull up an example. So here's an example from Rocky. This is something that we saw in class and many of you experienced as well. The 10-meter data should be silver. We should be in this zone right here where there's very little difference between the 10-meter and the LiDAR. And there's this kind of systemic shift toward the negative values, which is why the whole thing is drawing in tan. We couldn't really explain this. I don't know why this is only happening to some of you and not others. There is a way to get around this that we worked out in class, but I'm just curious what solution you guys came up with, or if this is something that's only striking certain systems. I don't know if it's a different version of ARC, if it has something to do with the root operating system, I'm not sure, but it doesn't seem to be affecting everybody equally, which is always a little bit freaky with GIS. So anyway, for what that's worth. So the reason I'm putting this kind of general set of slides together is because this was the important take-home message from this exercise. It's something that I would love to see someone tackle in a final project. If you're just freaking out about how awesome DEMs are and all the different ways you can display DEMs with their hill shades, of course, I think there's a ton that could be unpacked here from different coordinate systems, different resampling techniques. I think there's a lot that could be played with. So if you want to do that for your final project, go for it. Anyway, please let me know if you have any questions. I do have one final thing I want to throw at you. So going back to the DEM Mastery Lab and then the work you did with the DEMs of difference, these points represent the 4 different data sets. The half-meter LiDAR, the 5-meter autocorrelated, the 10-meter from the USGS, and the 30-meter from the USGS. And my challenge to you is to label each one of these points with those 4 different data sets. So on the x-axis, we have precision. So not accuracy, but precision. This is related to the resolution. Accuracy, completely different. Notice how 3 of the data sets are all fairly accurate and 1 is the outlier down here. So my question is, which data set is this? And the answer would be that this is our our half-meter LiDAR. It's highly precise with the smallest cell size, and we're going to call that the highest accuracy. This is the 5-meter autocorrelated DEM. It has higher precision, it has a smaller cell size, but it is far less accurate than the 10-meter USGS data and then the 30-meter USGS data. And the differences in accuracy here are not important. I just wasn't about to say that the 30-meter DEM was as accurate as the LiDAR. But this is the take-home message here. And it's not that autocorrelation, that process, is bad. Autocorrelation is the process that we use to derive incredibly intensely awesome DEMs from drone data, for example. So autocorrelation is powerful. It's also not the fault of the NAPE imagery. NAPE imagery is a beautiful data set that we can use for a whole lot of very important things. The problem comes in when we use NAPE imagery with the autocorrelation process. Putting those 2 things together results in very inaccurate DEMs. So, great big take home. Don't use these autocorrelated data sets from the UGRC to analyze your landscape. Don't use them with the hydrologic tools, for example. Big no-no. All right, questions, let me know.